we're going to look at question 9 off of week 2's tutorial. So the first question asks you for the given function f to calculate the partial derivatives f of x, x, y, z, which is equal to, we just differentiate each variable that involves x normally, so we get 6x, nothing from the y squared, nothing from the 2z squared, a minus y, and then plus 2z. The derivative with respect to y, we simply do again and we get 2y minus x, and similarly for the derivative with respect to z, and we get 4z plus 2x. So that gives us the three partial derivatives. We're now told that a surface has equation f of x, y, z is equal to 0. So that's our surface. And we have to find the equation of the normal line to the surface at the given point. So the normal vector, which is what we're after, at the point P, which is 1 minus 1 minus 2, is going to be grad of f at the point 1 minus 1 minus 2. So let's evaluate that. So grad of f at 1 minus 1 minus 2, well, that's given by the partial derivatives evaluated at those points. So we've got 1 minus 1 minus 2, so we've got each of those partial derivatives evaluated at the given point. And doing that gives us, we get 6 plus 1 minus 4 minus 2 minus 1 minus 8 plus 2, which gives us 3 minus 3 minus 6. So that's the normal vector. So the equation of the normal line is going to be, we're going to start from the given point, which was 1 minus 1 minus 2, and we have to add on a certain multiple of the normal vector. So that's our normal line. Right, we're now told the normal line meets the surface again at the point Q. Find the coordinates of Q and show that the normal line at P is also the normal line at Q. So first things first, we can rewrite the equation of the normal line. If I have R being x, y, z, I can also take out a common factor of 3 from here. So my normal line becomes 1 minus 1 minus 2, plus, taking out a factor of 3, 3t, 1 minus 1 minus 2. Now because t is just an arbitrary number, I can have that x is 1 plus t, y is minus 1 minus t, and z is minus 2 minus 2t. Remember, when we're interested in a normal vector, we're only interested in the direction it points, not how long it is. So those are my x, y and z coordinates of the line, so I have to insert that into the surface. So compute f of x, y, z, i.e. substitute x, y and z into the surface, and we know that that must be equal to 0 if we're going to have a point on the surface. So now that gives me 3 1 plus t squared plus 1 plus t squared plus 9 lots of 1 plus t squared minus 4 lots of 1 plus t all squared minus 9 is equal to 0. To help you see that, remember that the y is just going to be minus 1 plus t, and z is going to be minus 2 1 plus t. So now simplifying, this is all going to give us 9 1 plus t all squared is 0. So 1 plus t, sorry, that should be 9. So 1 plus t is plus or minus 1, which gives that t equals 0 or minus 2. Irrespective of how you've actually done this question, you should always get t equals 0, but depending on whether you made the simplification that I've done above with the normal vector, you may or may not get minus 2. Nevertheless, you should still get the same point. So q corresponds to t equals minus 2, and p is basically when t equals 0, i.e. when you haven't moved from the point P. So we get that q is equal to minus 1, 1, 2, i.e. what you get when you just insert minus 2 into the coordinates for x, y and z. So now we can evaluate grad of f at the point Q, and if you do that, you get minus 3. Oh, let's get this right. Minus 3, 3, 6, which is equal to minus 3, bracket 1, minus 1, minus 2. So we've got the same normal as before, so that implies it's normal to P, i.e. the normal line through Q is also a normal line at P and Q. The final part we haven't actually reached so far, and we'll deal with that next week.